Heat pumps. Anybody here miss Brian's class last week? Okay, we will review a couple things. Brian put together this slide for me, so my job was pretty easy. I can stand up here and go over my experience with heat pumps, testing in heat mode, and hopefully, if you pay attention, I will get less tech support calls in heating than I did last year, right? All right, let's see what he has on the menu. Oh, I literally used this already this week, so I don't know why you put that up there. It's kind of embarrassing. However, the facts speak for themselves, which is probably what this is all about. I am the best. This will be the best class you've ever been to. Instructor, mentor, life idol. Enough about me. And that's a joke we've used already. This is my family. That's a horse that's not mine. I spent 3 months on that in Canada. But in Canada, I learned the importance of heat pumps. Although they don't really use heat pumps for their winters out there. This is just some old material Brian had on here, which I'm not really sure. Okay, so back to heat pumps. Part 2, auxiliary heat. This is what he went over last time. I just wanted to hit a quick refresher before we cruise on, because this is all about heat pumps. And a couple of you weren't here. But testing our auxiliary heat to burn off anything that smells bad. Adriel rightly pointed out multiple times last week that the best way to do that is at the thermostat. And then if you are outside of some sort of limit, the thermostat has a limit for it or it's not engaging, find out why or jumper it out. You guys are doing commercial. You're not really going to be testing your heat strips on a commercial application and smoking somebody out inside of the space. If you're doing a maintenance and the space is being used, maybe not a great idea. The tech I used to ride with on the R2Us when he would do the heat strips, he would pull them out or at least visually look at them. If they had a lot of junk on them, he'd pull them out and clean them off instead of just burning them off inside the unit. So if they are coated in a lot of junk, you can get them clean without smoking out the inside of the building. Right? Okay. Heat strip, wire, and breaker sizing. This is crucial to not making an absolute disaster, and also just diagnostic problems like breakers tripping when they don't need to, things like that. So I have this up here just so that you guys know that the few of you that weren't here last week, that actually sizing your wire and your breakers exactly as a data tag lists for that heat strip is crucial for safety. But you don't always have to memorize this. You can use a data tag, and when you're thinking about wire size right here, which is really important, then you can either Google it or look it up or ask for this information. Just being aware that you can find it if you don't have it memorized yet, just being aware that you can find this information quite easily is crucial. Feel free to go back and look at the class for more information on that from last week. It was great, as Brian always is. We briefly talked about the 90-340 relay and the interlock ability so that you're always bringing the blower on whenever the heat strips come on. Another good reason for testing at the thermostat is to see how it responds, if it actually is bringing on the blower and if you have this working properly, right? Now, if you have your residential X13 blowers, then it just plugs into a different speed. So when white is energized, the blower runs at a different speed. So there's a lot of ways. You could tie in low voltage to this, the interlock, whenever the heat strips call, the blower calls. Or you could tie in high voltage through your blower. Not high voltage through your heat strips, but high voltage through your blower. Cool. All right, so we're going to focus on heat pumps, checking them in cold weather. Brian mentioned this last week, some of the concerns that customers have. Let's dive into here. You get these calls where people are freaked out and worried about the ice. And so here, this picture is a good demonstration of normal looking ice. versus not normal looking ice. And so I don't want to have any calls this winter from somebody who sees frost in their coil, and that's their version of a problem, right? We're going to get a lot of frost on our coil running in heat mode when it gets cold. When we get down below 40 degrees, we're getting in the frost area, right? And that's normal. That's what it needs to do in order to pull in heat from the outside air. So understanding that, don't panic when you see something different. I've never seen ice on a condenser coil before. That's fine. Let's just keep moving through and find out. Now, if you are caked in ice, as the picture shows on the bottom, that's a problem, right? Okay. So abnormal signs would be thick sheets of ice or completely no heat inside the house. This is another thing you can talk to the customer when you're going through your diagnostic problems. When it goes into defrost, what happens to the evaporator coil in our air temperature inside?
It would normally go back to cooling mode in defrost.
Yep. So it goes back to cooling mode in defrost. So your blower inside is now running through a coil that is in cool mode. And the purpose of that is so that outside your condenser that was the cold evaporator now has the hot discharge gas going through, melting the ice. But that means that inside the house, we're getting cold air. So it does activate your backup heat in order to like offset how cold that is. But you'll get that complaint. In the middle of the night, all of a sudden I felt this cold air. And so defrost usually goes for about 10 minutes, and then we come out of it. So an issue with defrost could be we don't actually have heat, a backup heat working, and so it's freezing air that comes out. Or it could be just less warm, and the customer needs to be educated on the fact that this is normal. And in Florida, we do a lot of education because defrost doesn't happen every year. Also, weird noises, steam. People talk about their unit smoking. They see the unit trying to run, but the fan not spinning outside. All that's normal, right? So you have a lot of ice that needs to melt really quick. There's going to be a lot of steam coming off of that, look like smoke. On here we have changes in airflow. Okay, they're just talking about the customer noticing the fan not spinning, the changes in airflow. If you do have your fan continuously running in defrost, it usually means that somebody just hooked the fan to the top of the contactor and bypassed the relay on the board. And it will still defrost, but it's much harder. Now you're working, the cold air is still being pulled against the coil while the hot discharge gas is spinning through. So it will defrost, but just a much slower process, less efficient. The customer is going to be stuck a little bit longer with the cold air blowing inside the house. Okay, checking charge in cool mode. What are some of the important changes in how you hook up in cool mode with your gauges when you're testing pressures?
You got a hook suction?
The
common suction?
Common suction, that's right. Why not just stay with the suction we normally hook up to in cool mode? Because in heat mode, it's a discharge. So let's talk about what happens, what changes in our heat pump when we're actually switching from cool to heat. So in cool mode, we have our condenser coil outside where the hot discharge gas gets cooled down and it displaces heat into the outside air and it turns into a liquid, pumps inside to our evaporator where our evaporator is really cold, it's absorbing heat. And then that pumps outside on our suction as a superheated vapor. And then we repeat that cycle. The reversing valve actually shifts the direction of refrigerant going to your evaporator coil and your condenser. So now the compressor always sucks in the cold vapor gas, always discharges the hot vapor gas. So nothing in the compressor gets switched. The direction of flow into the compressor, the direction of flow out, you always have a discharge line coming off the top of that compressor. You always have a suction line going into that compressor. But the rest of the system gets switched. The reversing valve redirects the flow of refrigerant, and we actually are now pumping our hot discharge gas straight out of the compressor into the suction line, the one we can normally grab and it's cold, pumping it straight to the evaporator coil. And once that evaporator coil is blazing hot, the cold air of the house is coming across it, it's getting rid of its heat into the cold air of the house. So now we've effectively turned our evaporator coil into a condenser coil. Yep. But we still need to grab heat from somewhere in order to produce heat. So we are grabbing heat from our outside air. And in order to do that, that means that the coil outside needs to become an evaporator and be lower in temperature than our outside air. So if we're trying to grab heat from 35-degree air, our evaporator coil and the refrigerant in it is going to have to be colder than 35 and significantly colder in order to be efficient than 35 degrees to grab whatever heat it can. And you take that heat, let's say it's 35 degrees outside, and you've absorbed it into cold refrigerant, and your refrigerant is probably more like, after it's absorbed the heat, it's probably more like 20 degrees, maybe 25 degrees going into that compressor. You can't really heat a house with 25-degree anything, right? So that's the magic of the compressor. You have all the heat energy there. Now it just needs to smash it and compress it and activate all those molecules, get them angry, get them moving, the friction, and we have high temperature that we can work with. Same energy, same heat that was outside in your outside air gets pumped inside, but at a high pressure, high temperature. So the important thing to note on this, your outside is now your evaporator coil. Your inside is your condenser coil. So when you hook up your suction, big, large suction line, it's going to always be your discharge. And then your liquid line, what's that going to be now?
Liquid line.
Your liquid line, exactly. The difference is the direction of flow, not that it's not liquid. So more accurate on a heat pump is to call the suction line the always vapor line, because if it's discharge or suction, it's still going to be vapor. So you could call the vapor line liquid line, right? Okay. Common suction port, what does that tap into? Where does that little tiny common suction port on a split heat pump go back and tap into?
The common section come out the reversing valve.
Right before it.
Right before it.
Before the reversing valve, yep. So the suction before the reversing valve, which is your common suction. Yeah, as we talked about already, the compressor always, there's nothing changes with the compressor. So it taps into the suction somewhere between the compressor and the reversing valve where things don't change, right? And then let's talk about the difference in hooking up between, like, say, a Carrier system, Trane, Lennox, or literally any other system. There's a few Goodmans that are the same as the Carrier, but right here in this picture we have our Carrier setup. And where's our metering device?
On the liquid line, sir.
Yep, right there on the piston. And if you look at the direction of flow, we're flowing into the condenser. We're hitting our piston before we actually hit the port, the service port, which means that if we try to get an accurate reading of our liquid, we're not going to be able to hook up there. The piston is going to restrict the flow, so we're going to have a pressure and temperature drop before we actually have that service port. So in the other direction, on a setup like this, where you have the piston there, that liquid line reading becomes obsolete. Don't try to use it and get confused in your diagnostic, right? So you don't actually have a liquid. Typically, you don't have anywhere to read liquid in that situation, which a lot of you commercial guys doing RTUs and package units, that's pretty common to not have a liquid access anyway. And so then you'll notice on this, the manufacturer is going to have a chart that looks like this, and it'll give you high pressure, low pressure readings. And so that high pressure is your discharge gas. Now on the suction, that's where your high pressure goes. The low pressure is the common suction port. And then on every other setup, what do they use as a metering device?
We have TXVs.
TXVs. Yeah, so TXVs are going to typically be inside the condenser. And if you're wondering if it's a piston or a TXV, look in the condenser, follow the liquid line. If the liquid line doesn't come into a TXV, we have a piston in this flared connection piece here. It's not actually a flare. I forget what it's called now.
Chapel.
That's great. I'll take that. Thank you. So we are actually, even Carrier and most manufacturers are moving away from the piston altogether. We're seeing a lot more TXV. So that means if you do have a TXV, you can actually hook up to the liquid port and have an accurate head liquid pressure reading. You can actually check subcool if you have that. Just it's important to be aware of this so that you're not confusing you on the situations when you don't have that and all you have is your discharge and suction. So let's go into checking charge in cold weather. Is there anybody in here that feels uncomfortable with accurately checking heat pump charge in 40-degree weather? Okay, 2 people. The rest of you feel great about checking charge in heat? That's good. All right, so you guys can all leave because the rest of this class is going to teach you how to accurately do it. But since you all feel comfortable with that, you can leave. I've never felt so unneeded and hurt. First thing on here is not just the thing that you say because you need to be accurate and you need to like make all the nerds happy online, read the manual, check manufacturer specs. No, that's absolutely essential in a heat pump in heat mode. There's a lot more variance between one model and the next in heat mode than there is in cool mode. So things like the evaporator, if it was sized for our climate where it's oversized and does more dehumidification, can affect your head pressure quite a bit. And then things like how efficient the coil is outside. Whether you have an older little tiny baby or you have the ones designed for really efficient heat pump, really tall stack coil, same tonnage, you're going to have different readings. And so manufacturers are really great, actually, about putting charts either on that back panel or if you open the install manual, even a more thorough chart that can walk you through what your pressure should be in heat mode. So for me, usually typically at the early of the season, I'll snap a picture, not of R22, but of a 410A chart like this, because I can get kind of a general rule of thumb at a glance from a chart like this. If it's this temperature outside, this temperature inside, general rule of thumb. But we're not going to have exact numbers unless we actually look at that manufacturer. Lennox is great. They actually talk you through how to test it when you need to recharge it. Covering the panels outside, they walk you through doing that. When you actually need to add charge. And then Train, they have also, well, this is more about defrost, but they have step-by-step testing defrost. They have a demand defrost, which is a little different than their carrier setup. And then at the same time, plenty of charts for checking heat mode and what to expect on your liquid. And that's another thing. A chart like you're seeing right here is for this picture before. So this is discharge, common suction, whereas if you hook up to a Lennox, the charts that the manufacturer give you is going to be liquid. Also in there, they're going to say below this temperature, you're going to need to check your charge in heat. Above this temperature, check your charge in cool. Anybody know where that common point is? So it's typically 60 to 65 degrees. So I want to say to you guys, if you're above 65 degrees, let's turn it in cool mode. And we're going to set charge and check charge that way. It's probably a little bit more accurate. If you're below 65 degrees, let's turn it in heat mode and figure out what we have there. And so then next thing, let's talk about some rules of thumbs. Rules of thumbs are just that. Everybody has a little bit different size thumb. Point is, it'll get you close, but not exact. And so close is often good enough if you're doing, let's say, a maintenance, and we don't have a complaint. Close is good enough if you do a diagnostic call and you have a failed capacitor, and you need to make sure the system's actually operating the way it should afterwards. We don't have a reason to be suspicious of our charge. Close is not good enough when we're doing a quoted repair, and we need to recharge our system. Close is not good enough when the issue is a refrigerant-related problem. We need to make sure we actually set that refrigerant exact. But the rule of thumb is really great for letting us know if we're in a safe range. Let's talk about this first and most common one, the discharge vapor line being 100 to 110 degrees over ambient. Anybody here notice that that's not true?
It's been around for a long time.
That's exactly right. If you check this regularly when you're checking heat pumps, you're going to notice this is very inaccurate unless you've let it run for a long time on a cold day. And so the issue is that on a cold day with our refrigerant temperatures as low as they get, you can have a lot of liquid that collects and builds up in the accumulator from the last run time, and you turn it on and a majority of your refrigerant's not actually in circulation yet. And so running it for a long time, letting it stabilize is key for this particular one. So the 100 degrees above the ambient. So ambient outside, 100 degrees discharge. Take your discharge temperature right there on the suction, what was the suction line, and then outside temperature. That's also what they're using on this chart. They also have the wet bulb, dry bulb, wet bulb slash dry bulb up at the top, and you can see the two temperatures at the top. So it would be more accurate to use wet bulb. Find the wet bulb on the chart would be a little bit more accurate than dry, because there's a lot of heat and moisture that's being held. So if you account for that, you get a little bit more of an accurate reading. Okay, systems must be frost-free and outdoor temperature must be between 65 and 15 degrees. And so that is another range we just talked about, but we didn't talk about the low side. If you're trying to go off of rules of thumbs, once you get lower than like 15 degrees, you're not going to be. None of your rules of thumbs are going to really apply. And the reason for that is that you have to bring the suction pressure so low in order to get it cold enough to absorb heat from a 15-degree air that you're actually going to change your compressor ratio quite a bit. You have hardly any gas feeding into that compressor, but it's still slamming out really high pressure on the other end. The inside of your house maybe is 68 degrees, and so it's still slamming out a very high pressure. It still has to produce that same on the side, but we're pulling in a very small amount of refrigerant on that side, so we don't have as much for the compressor to work with. So it changes the compression ratio, and this, especially the discharge temperature over ambient, those things aren't rules of thumbs, just go out the window. So what do we do when we can't use a rule of thumb and we need to get our charge where it's supposed to be?
Use a charging jacket.
Charging jacket, that's great. You have a charging jacket. What else? What would be the best way? 15 degrees. We need to get our charge right. I knew this was a good time for breakfast.
Way out the charge.
Someone say no yet. Way out the charge. Way in the charge. Right? So install, quota repairs, things like that in very cold weather where we're making significant changes to the charge. Let's wait out. That's crucial. Okay, let's say we come up to a system and we have like an 80 degree above ambient after 25 minutes of running on our discharge. Any clue what might be causing that? Normal indoor temperature, let's do 68 indoor temperature. Instead of our 100, we have a little bit lower. That typically means you're overcharged. So you have a little bit more refrigerant the compressor's pushing against, but also a lower compression ratio. So you'll actually have a higher discharge temperature when the compressor can smash it a little bit tighter. Maybe a little less refrigerant coming in. Initially coming right out of the compressor, you're going to have a little bit higher temperature. So when you're overcharged, you're going to see this number come down a little bit. You also will see it go above when you're undercharged. So it's a little counterintuitive, which is why I'm talking about it, but we have 130 degrees above ambient, we're probably undercharged. The other thing to keep in mind is if you're grossly overcharged, then that no longer applies. If you are significantly overcharged, you're going to have a really high discharge. Your compressor's just fighting against. So that takes quite a bit. So do keep that in mind. If you have a reason to suspect somebody added an extra 10 pounds to your unit. Okay, liquid line temperature above indoor dry bulb, 3 to 15 degrees. This is approach. So indoor is the temperature coming across your condenser now, which is inside. So that's a reference points that you're going to use. Normally with approach, we're taking outdoor temperature and liquid line. But with approach and heat mode, you're taking indoor temperature and liquid line. So this is another good rule of thumb. Another good rule of thumb not listed on here before is that, oh yeah, suction line. So This would be hard for us to read on a split system because the suction line is behind the reversing valve. But on a package unit or an RTU, you have access to your suction line. So suction line 5 to 15 degrees below outdoor ambient, you're in a safe range, rule of thumb. So, and a lot of these you want to take them together. If you have good charge and you have one of your rule of thumbs hitting the target and you do have good charge, you're probably going to have your other ones hitting the target as well. But if you just have one hitting your target and the others are way off, we have a problem. We need to do more investigation. Another one not listed on here is that typically within our range, I would say, of about 20 degrees and 65 degrees, you're going to have 20 to 25 degree saturation below outdoor ambient. So we have our outdoor ambient, then it's going to try to drop our pressure so that our suction saturation is 20 to 25 degrees below that, so it can absorb the heat. Which means if it's 35 degrees outside, how cold is our saturation going to be?
10 to 15.
10 to 15, which means the second it comes on, we're going to see that frost, we're going to see that ice. Because it's trying to hit that 10 to 15 degree refrigerant level and absorb heat. We're going to see that frost right away. That's normal. And immediately your system's going to be triggered that the defrost trigger is going to immediately go off, and that timer is going to start counting down. You set a timer on your defrost board for how long it notices that we're below freezing before it kicks into defrost mode. So in Florida, we usually set it for the max, which is like 90 minutes. So it gives it a chance to run that long, even though the sensor is sensing that it's freezing, and hopefully satisfy the house and turn off and stop freezing before it engages our defrost. Using the charging jacket. The charging jacket, Fieldpiece has a great charging jacket. You wrap around the unit, strap it down, and as the heat, so using a charger jacket would be when you turn it into cool mode on a system, because it is more accurate to check refrigerant in cool mode. So one test that you can do is turn it into cool mode and use a charging jacket. Have you guys, anybody here not seen a charging jacket? Oh, okay. Wow. Okay, I should have put a picture in here. My bad. But basically, it's this black bag, this charging jacket that goes over your condenser and wraps down the sides a little bit. So that when you turn it in cool mode, the hot air circulates back into the condenser. And then it brings the pressure up a little bit more, raises the temperature of that air, keeps that circulation. So you can simulate a cold, somebody twitched and I realized what I did, simulate a hot summer day. We got that hot air circulating and you watch your head pressure come up to what you would normally see in cool mode, and then you can more accurately check refrigerant charge in that way. And like I said, Linux has even like a breakdown description. They don't want you setting the charge in heat mode. They don't even want you trying. So like if you got to adjust the charge, wrap it. They talk about wrapping it in cardboard and making adjustments as your head pressure comes up to a normal level. That's it for today's class. I did want to take any questions that you guys have or scenarios that have been issues. We're already at our 30-minute limit, but we can keep going with questions. Or
What would be a good temperature split you'd expect to see?
Great question. So that's also a huge range because the load affects that so much. As outdoor temperature comes down, you can't produce nearly as much because your compressor is being fed such a low volume of vapor. And so you're going to see a huge swing. I've never seen anybody list it as a rule of thumb because of that. So probably forget about that. I've seen like 35 degrees, and then I've seen like 10 degrees in testing it. So, well, the 10 degrees was low in charge. I've never actually tested something when it was about 10 degrees outside. It's never gotten that here. So that one was more low in charge, but you probably will never see something that low with a decent charge here. Unless you're working in North Florida, possibly, and you got 10 degrees outside, then you'll see some of those extreme changes. There is a general rule of thumb of like 60 degrees, 40 to 60 degrees condenser saturation above ambient. So your indoor is now your condenser ambient. But again, that's another thing that ranges quite a bit. So when we're talking about rule of thumbs, I guess it is important that I actually do mention this. When we're checking it's going to be really important that our system is maintained, clean, and operating normal before we can trust the rule of thumb, right? So if our condenser coil is clogged at all, like even a little bit, we get away with it in the summer. But when you go into cool mode and you got to absorb heat through that coil and it's 30 degrees outside, that's going to be a real problem. That coil is going to want to freeze outside. It needs perfect airflow across that coil. So that's a thing you watch for. I will sometimes spray a coil when it's cold outside just to make sure I don't see dirt coming through that coil and we're not being affected by that. And also the water's around 70 degrees, so it allows me to bring the temperature up a little bit and see something a little more normal for a second and feel better about myself. The other side of that is your evaporator coil is a much smaller coil than your condenser. So it's very affected by your indoor blower, and it's very affected by being dirty as well, or your filter. We're already dealing with a smaller coil, so it's going to be higher pressure. Same amount of refrigerant is trying to condense in there, but we have a lot higher pressure typically. So if your blower is set for a low speed because somebody wanted to dehumidify really well in the summer, and so we just dropped it down to a low speed, you could run into issues in the winter with it going out on high head, really high temperatures across that coil, or the filter starts getting dirty and the combination is way too much, and we're going out on a high head pressure. So keep in mind your blower speed, your filter, and then lastly, if that coil's dirty, one, it's pretty disgusting. That coil's going to get very hot. You're going to have like 140 degrees on the surface of that coil, and it's going to bake whatever nastiness is in there, and typically you're going to smell it. So that's nasty. But on the flip side, of course, a dirty coil is going to create really high head pressure as well. Something that may be 30% impacted. We went through the summer fine. We never noticed it. We didn't care. And now in the winter, we're going out on high head. So keeping those things in mind. Airflow is crucial both outside and inside. Thanks for asking that split question. I forgot all about airflow. Great. So if you didn't hear anything else, you heard that if you read the manufacturer specs, they give you some pretty great information on heating. They give you more information on the heat and checking it and charge and rules of, that can help you like practically than they do on the cool, because they understand that heat pumps are a little surprise to technicians more often than cool is, right? So great, thanks.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. Also, don't miss out on our free mobile applications available for both iPhone and Android. They're packed with handy tools and calculators to make your job even easier. And while you're at it, join our thriving Facebook group. We're all about community. Vortex by Tex.